free fall is the same as weightlessness. So let's talk about that. So there's a lot of misconceptions about weightlessness. But when I say the word weightlessness, this is an object like you and me, or a ball, that is in a state of free fall. And again, there's a lot of misconceptions about this. And to try to give you a feel for this, what I want to do here is that I want to give you an analogy. Okay. And the analogy here is that we're going to imagine that you're riding an elevator. So you're a person in an elevator. So when I imagine this, here's my elevator right here. And what we're going to do here, and there's the cable right there. And what I'm going to place on this elevator is I'm going to place a weight scale. So I'm looking at this elevator right here. And what I'm saying here is that this thing right here is a weight scale. Okay, so I have a weight scale. Now you're going to be standing in the elevator. So if you stand in the elevator, you're going to be looking something like this here. Maybe your hair is long. Okay, so that's the situation that we're in here. So what we want to do here is that let's look at multiple cases of what happens. So the first thing that we should say here is that if you are at rest on the weight scale, let me be careful here. That's not what I really mean. So I got to erase that. Sorry about that. I did not mean to do that. If the elevator is at rest or moving at constant velocity, what you're going to find here is that the scale reads a normal weight. So what I need to do here is that now I need to now define here. So I'm going to say that the weight of person is, of course, the force of gravity, and we're going to say that's 500 newtons. So that means if you're standing if the elevator's at rest or moving at constant velocity, the scale reads a normal weight. So what number is that going to read? 500 newtons, right? So the force of gravity is 500 newtons. Now we want to look at other cases here. And what we're going to do here is that now the elevator is speeding up, going upwards. So now we have an elevator speeding up, going upwards. Okay. So what do we know when this happens here? What we know here is that you are either at rest or moving at constant velocity. If the elevator speeds up, then you want to stay at rest according to Newton's first law, or moving at constant velocity. So in order for you to catch up to the elevator has to apply a force on you. So in essence, the elevator has to apply a net force to accelerate you. So what does that mean? You feel more. But that's the same as you feel heavier. You feeling that force means that the force of gravity, the weight scale, has to push harder on you. So as a consequence, what you find here is that the reading on the weight scale is larger than 500 newtons. So you literally read a larger reading. Now we can do the same thing going down. And by the way, when the elevator, especially if you get one of these fast elevators, like some of the elevators in New York City, when it takes off, you can feel your knees buckle a little bit. And that's because you actually have a higher weight reading at that point. Now, let's look at an elevator speeding up, going downwards. So I'm going to move this down a little bit because I need the space. Okay. So when you go down, what you find here is that the elevator has dropped. But according to Newton's first law, you're still at rest. So all of a sudden, the elevator doesn't have to push up as much. So what I'm saying here is that the elevator suddenly drops down, but N1L claims you are still at rest. So then this implies here that the elevator is pushing up with less force. But wait a minute, what does less force mean? That means you feel less, and if you feel less, that's equivalent to saying that you feel lighter. You feel lighter. So as a consequence, what we're seeing here is that the reading on the weight scale is now smaller than 500 newtons. So you would read a lower reading for your weight. So to try to get you, so it's this falling that I'm really getting at right now. So when you're falling down, you feel less weight. So the question is, why is there even a weight scale reading? And here's where I'm going to bring in an episode of Homer Simpson, because my oldest son loved The Simpsons. So he was a religious fanatic on The Simpsons. And he showed me this show, and I thought this was really well done. So what we have here is that we have Homer. He had just drank a lot of beer. And he was reading about weightlessness, and he decides to test it for himself. So what Homer does is that he jumps from the second floor balcony into a pool below. So what do I mean by that? Well, I could imagine that we have a 2-story house. Okay, so this is the 2-story house. And when I look at this house here, according to him, there's this balcony right here. Okay, and this is the edge of the balcony. So when I'm looking at this house here, what I see here is that down below, here's this pool of water. Right? So here's the pool. Now, what happens here is that Homer, just like the elevator example, had what? He had a weight scale. Right? So we know that right here, this guy right here is the weight scale. And what he did here is the weight scale was duct taped to his feet. And then here's Homer. So he's standing here, right? And his feet have now been duct taped to it. And then, of course, Homer has that good sized belly here. And so what you're finding here is that then Homer jumps. So he jumps into the pool. And the question goes like this. What does Homer read on the weight scale as he is falling? And the answer is he reads a 0 weight reading. He doesn't read anything on the weight scale. And so then, of course, our next question to try to answer this is this. Why does the reading on the weight scale read 0? And the answer is there is no ground pushing up. And so what you want to do here is that you have to have the following scenario here. So what you want to do here is that imagine that we have the ground right here. So we want to do a series of arguments here, right? So we know this is the ground. And what are we going to put on top of the ground? We're going to put the weight scale. Right? So there's the weight scale. So when I look at just those two here, if they're in static equilibrium, what I see here is I see the following thing. I see that right here, I see that I have what? The weight of the scale. And then I see the force of the ground. Okay, so that has to be the case. So because they're in static equilibrium, we then say here that the force of the ground must be the force of gravity of the scale. So now what we're going to do here is that we're going to do the exact same thing here. So now if I take my weight scale again, this time I'm going to put Homer on here. So here's Homer. And so when you're looking at Homer, what's happening to Homer? Well, Homer is standing on the weight scale now. And what happens here is that when we read the weight scale reading, what's holding up Homer? Well, that's really the force of the scale. So this is what's going to be reading Homer's weight. And so when I look at this situation here, now what I see here is that this is now the weight of Homer. So what you're finding here is that what's the role of the ground here is to push up on the scale. And so if there's no ground, then the scale can't push off the ground. And so what you find here is that the ground now pushes up on the scale. So then the scale pushes upwards on your feet bones. And you feel that. Then your feet bones push up on your ankle bones. And then your ankle bones push up on your shins. Your shin bones push up on your knee bones. And then you could just go all the way up here. But the most important thing there is the ground. The ground has to push up on the weight scale. So what you're seeing here, so without the ground, you can never have a reading on the weight scale. So without the ground, the weight scale cannot have a reading. So when Homer jumps, there's no floor to push up. So when he looks at the scale, he reads 0. So what I'm saying here is that if there is nothing to push up, Homer feels nothing because the ground is responsible for you feeling the force of gravity. So he feels nothing. So what we say here then, a weight scale in free fall will always read 0, and that's what we mean by weightlessness. So that implies weightlessness. But that's a misnomer, right? That's a misnomer. And the reason why that's a misnomer here is because when we talk about weight, we talk about the force of gravity. So if I come over here to this word called free fall, what does free fall do? This implies that the force of gravity is causing Homer to accelerate, right? It's causing Homer to accelerate. So it's not that there's no force of gravity. It's just that the weight scale will read 0. So then if I was to define weightlessness, I would then say this here, is that weightlessness, I'm just going to summarize what the previous paragraph says here. It's a 0 reading on a weight scale during free fall. So people will say that you don't weigh anything, but that's not true. You still have mass. You still have a force of gravity acting on you because you're falling, you're accelerating. So that's what I mean about weightlessness. A lot of people don't realize that free fall and weightlessness are effectively the exact same statement.